ODE stands for ordinary differential equation. Given ODE with initial conditions, dy dx is the ODE, and the initial conditions can be x equals to x naught and y equals to y naught. So these are the initial conditions. Sometimes we will just abbreviate this as YE, IC. Initial conditions, so ODE. The iteration formula Okay, turn that mic off, please. Somebody's making noise. Don't make noise with the mic on. So yn plus 1, the iteration formula is yn plus h multiplied by t4. T4 is a function of xn, y of n, and h. So this is a function of. So it's a function, it's not multiplied, it's a function of. The formula for T4, now I'm talking about this T4 here, T4 is 1 over 6 K1 plus K2, 2K2 plus 2K3 plus K4, K1 fxy, K2 is f x plus h over 2, y plus h over 2, K1, K3 is defined to be f as a function of x plus h over 2 y plus h over 2 K2. K4 is a function of f x plus h y plus h K3, and h is the step size. This is defined to be the step size. The basic step size. Okay, let's do an example. When we do the example, you'll know what's going on. Example, given the ordinary differential equation 3x squared y, and the initial conditions x naught is 1 and y naught is 2. What it means is, what it really means is like when x is 1, then y is 2. That's what it means. So use a step size 0.1. Now what we're going to do, you are given an initial point, like for example, let's say you are given a point here, 1, 2. Okay. So now if I ask you to find what is the value here, call this x1. Okay, this is like x naught and then y naught, right? So if I ask you to find x1, which is going to be which is going to be like, x1 and then the corresponding y1, the numerical value. So this is going to be like, let me put this in a different color. This is xn and then yn. Here is going to be xn plus 1, yn plus 1, the next point. So if the step size is 1, sorry, the step size is 0.1, and then the next point is going to be like here 1.2, for example. Sorry, 1.1, because the initial point is 1, right? 1 plus 0.1 is 1.1. The y point, initial point is 2. 2 plus 0.1 is going to be 2.1. Okay, this is like finding, this will give you y1. What is y1? Once you choose your x1, then you can find y1. Then you can go ahead and find other points. You can find y2. Okay, so y2 will be y2 is the point when you increase the step by 0.1. So it's up to you how many points you want to find. If you want to just find y1, y2, and so forth. In this example, we'll just find y1. Just additional. Okay, using that formula, y1 using this formula, let's bring this formula over here. Y1 is, we're going to find y naught, n plus 1 is 1, y1. Therefore, yn must be y0, y naught plus h. T4, x1, y1, and h. Sorry, not x1, x naught, y naught. Okay, guys, are you all able to follow?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay, the rest is we just have to plug in the numbers. Now we go back to this formula here and find y1. Sorry, we go back to this formula to find the y1. And then we know from here your T4 is given by this equation. Your T4 is given by this equation. A T4 this for reference. Leave it here. T4. Therefore, replace that T4 in your equation. Multiply by 1/6 K1 plus 2K2 okay. In this case, your age. Okay, let me wrap. Okay. Your age is 0.1. Okay. Next, what you need to do, and also your y naught is, what is y naught? Y naught is what?
Two, sir.
What? Okay. Okay, y naught is 2. A1 is f x naught y naught. We already defined everything here. We can just bring this over here for reference. I just put this on the side here. So K1 is x, is f function of x and y. So the K1 here is going to be fx naught y naught. The initial points. So let's calculate what is here. K1. This is the equation that you're going to use right here. 3x squared y. So we know we define your differential equation as fxy. Just bring it over here for reference. fxy. Okay, so K1 is fxy. That's going to be K1 is fx naught, y naught. And that's going to be 3x naught squared, y naught. What was x naught? 3. X naught was 1. Y naught is 2. So what is that going to be? K1 is
6.
okay, 6. Now K2. Go ahead and refer on the side here. K2 is f x naught plus h over 2 plus y naught plus h over 2 K1. X naught is 1, right? This is 1. This is 1. And then this is 0.1 divided by 2 is 0.05, right? And this is 2. This is 0.05. And then K1 is 6. Therefore, K2 is going to be F1 plus 0.05. Okay. Just 1 plus 0.05 is 1.05. Then you have here 6 times 0.05 is how much? 0.3 times 2, sorry, 0.3. What is 0.05 times by 6?
0.3, sir.
0.3.
Yeah.
Okay, 0.3. Then 0.3 plus 2?
2.3.
2.3. Okay, now you have your x and y points. You go ahead and plug into that formula for k for the equation. Okay, so that's going to be 1.05 squared multiplied by 2.3. Okay. So that's going to give you how much?
7.6073.
Okay, thank you. Then K3, similarly, you repeat the same thing. All these are basic algebraic kind of work. So K3, if you look, is going to be F x plus h over 2, same as before, right? And then on the other side, it's not going to be the same. It's going to be y plus h over 2. I'm looking at this. Y plus h over 2 times K2. Y plus h over 2. H over 2 is 0.05 times by K2, which is 7.6073. So that's going to be F 1.05, 7.6073 multiplied by 0.05 is
2.38.
how much?
2.38, sir.
Okay, thank you. So you plug into the formula, you get 1.05 squared multiplied by 2.38. So that's going to give you Janeson, who can answer this other than JJ?
$7.871, sir.
7 point?
871.
Are you sure?
Yes, yes, sir.
Yes, sir.
K3,
Yeah.
Yes, sir.
7 point?
87185.
871. So 87185. 87185.
85. Yes, sir.
To 4 decimal places. Okay, good. K4. The other guys, please wake up and keep your calculator there, pencil and pad. Okay, don't you hide behind the screen and playing on your WhatsApp or Facebook. K4 is going to be fx plus h. Fx plus h. See here, K4 is just fx plus h. X plus h is 1.1. And then on the other side is y plus h times K3. Y plus h times K3. So, okay, somebody else other than those guys who have answered this, who can ask? Walalmadi, what's the 2 plus 0.1 multiplied by 7.8719? Okay, someone answer, please.
2.787, sir.
2.787.
Yes, sir.
Yes, sir.
1.1,
Yes, sir.
2.787. Okay, good. 2.287, right?
787.
787.
That doesn't make sense. 2.787.
Yes, sir.
Yes, sir.
Then 3 times 1.10 squared, 0 squared, multiplied by 2.787. What's that equals to?
10.1168.
10.116.
Okay, 10.116, 10.116.
Eight.
Yes.
68. Then just let's put 10.11768. Okay, fine. So you already found. Thank you guys for your participation. Okay, so you got everything to find y1. So let's bring this formula down here for reference. So you got everything to plug into this equation and evaluate y1. 2 plus 0.1, 1 over 6. K1 was calculated as 6 plus 2, K2 K2 was 7.6073 plus 2K3 plus 2K3 is 2, K3 is 7.8719 plus K4 is 10.1168. Tutup. So if you calculate, you'll get somewhere around y1 is 7.787. X1 is 1.10. So that is the answer. If you just want to find y1, that's all. If you want to find y2, say you want to find, repeat the process, repeat process to find y2. So to find y2, the equation will becomes y2 is y1 plus ht4 x1 y1, where k1, I know, and then, yes,
So y1 will be 2.78, sir.
y1 is 2.78,
Yes.
7. Okay,
2.78.
okay, thank you very much.
Let us see.
Do we know how accurate this is? Do we know how accurate our answer is? Do we know? Okay, do you know how to find the exact solution? The exact solution is to solve this equation. We have solved ODEs in our previous mathematics courses, right? To find exact solution. The earlier one was the numerical solution. Now you find the exact solution. You guys know how to do this? I'm pretty sure you know. Maybe if you have forgotten, this is separable equation. Okay, 3x squared dx. Correct? Separable, right? Separable.
Yes, sir.
Anybody saying no, sir? Okay, what is the, now then you integrate both sides. Integrate the integral of 1 over y is ln y is equals to 3x cubed over 3 plus c. That's going to give you ln y is x cubed plus c. Now we're to, you can solve y. Y is going to be e to the power of x cubed plus c. So that's going to be e to the power of x cubed multiplied by e to the power of c. Okay, this is a constant. You can just call this k or something, a constant. Or you can simply, you can call it any name if you like. If you, because I don't want you to go confuse with the other case, you can call this C1 and then C1 and then C1. And e to the power of C1 is another constant. So you can call C2. So y is C2 e to the power of x cubed. Is this solution right? If you want to check whether this is right, then we have to plug in the initial value. The initial value y is 1, right? X equals to, x naught equal to 1, y naught is equals to, are we getting 2? We want to find out, okay? The x naught is 1, what do you get? But before doing that, we have to use the initial conditions to find what C in 2 is. The initial condition x naught is 1, e to the power of 1 is equals to, y naught is 2, sorry. Then from here, you know, you find out C is equals to 2 over E. C2 is equals to 2 over E, right? Is it? Two over E. Do you guys agree? Hello? Hello, guys? Are you all,
Yes,
Yes,
sir.
sir.
Yes, sir.
okay, so we
Yes,
made a
sir.
mistake there. So we made a
Yes, sir.
mistake there. So
Yes,
it's
sir.
supposed to be 2 over E here. Okay? So that's the equation. Now you evaluate that equation at the initial condition when x equals to 1. So you know this is a 2 over E here. So therefore it checks. So that's a way to check if you have derived the equation correctly. So E and E cancels. E and E cancel, so it end up with 2. So after you come up with the equation, you need to first check the initial condition, whether they check or not. Your equation itself is wrong, then you go and try to evaluate at point, at a step 1.1, then you'll get everything wrong. Then you start calculating, you thought there's algebraic error, you start calculating and again, it will be wrong because to begin with, your equation is wrong. So now let's go and try to do at x n plus 1. X at n plus 1 is 1.1, right? x1, x1. So this is what you got from numerical analysis at x 1.1, x1 1.1. Just to put it here by a side, from numerical analysis, this is what you got. So x1 is 1.1. Now you plug in into this equation that you, into the exact equation. You put 1.1 into the exact equation. We get 2 over E. E 2 over E 1.1 cube.
So it's 2.784.
2.784.
784.
Okay. That is the exact solution. So this is the exact solution. And this is the numerical solution. Percentage error is your exact solution, or whichever way is fine. 2.784 minus the numerical solution, exact solution minus the numerical solution divided by the exact solution.
Got it, sir.
See, I'm getting like 0.01, 0.010.7 multiplied by 100. Is equals to 0.10 0.10. That's a lot of a big percentage. Approximately 0.
Sir, I get 0.107, sir.
Okay. Gitana. Who's
Pavitran,
this?
sir. Pavitran.
Okay. Okay, thank you, Pavitran. That's what we are getting. The percentage error is like around 0.1%. To be able to get very accurate answer, you should be able to, for more accuracy, so now we can express this in more decimal places. In many decimal places, you get more accurate answer. Later, we'll show you an example. Lecture, so now I'm going to show you a program. It's a MathCAD program that I wrote to evaluate the above problem. Whatever I'm writing by hand, I just put this in MathCAD. Okay, but in MATLAB, they have Rungge-Kutta toolbox. They may have engineering mathematics toolbox. Here's one example. Okay, before you do that, I would like you to do your assignment on this. Let's see. Assignment. I mean, this is not a separate assignment. This is an assignment, same assignment 1. This is part 3. So each time you do your assignment, then you can just compile and send to me later. Don't keep it at last moment. Try to do it every day. I'm just giving you very little at a time. Assignment 1, you try to, okay, let's talk about this program first. Okay, guys, it's the same problem that we did there before. So you are given a differential equation with the initial conditions. This is the differential equation, the dpq. It's the initial condition. You can solve this problem. You can get the exact solution of this problem. It's the exact solution. You can easily get this exact solution by just integrating, just like you can either do separation. If you cannot do the separation of variables, then you can do other methods that we have learned. In maybe you can go use integration factor to do this. So this is an example just to learn how to solve and find y. This is for just practice. So now we do the numerical analysis and then we find the solution. Our interval that was given here is h.8, h is 0.5, okay? So your t1 is 0.5. If you continue, or you also can continue with t2, okay? So we only did until this, right? Ours we call y1. It's called w1 here, okay? So if you want to do, if you want to continue and find other points, get other solutions, then you have to, this is like t1 plus 0.5. That gives you t2. Okay, then next one will be t2 plus 0.5. Okay, so you can find numerous other solutions for the differential equation, for the ODE. This is just for your reference. But in our example, we just did y1. This is called w1. In our case, we call this y1. y1, okay? We just follow the method we did in our class. For Rungge-Kutta, there are different methods. This method that we used is called Rungge-Kutta. Did I say Rungge-Kutta? Say Rungge-Kutta, 4th order Rungge-Kutta. So if you do by hand, this is what you get. This is the exact solution. This is what I would like you to do. You put, but for your case, you're just going to do for the first part, and you're only going to do for y1. This is y1. Maybe y1, this is like y2. This is y0, this is y1, y2, y3, and y4, something like this. But I'm just asking for y1. Do the numerical solution for y1, and then find the exact solution for y1, and then calculate the error, okay? you put your answer in a table like this. Or you, okay, you should have just these two. Just these two only. The comparison of the exact solution with the numerical solution with the initial condition when x naught is plugging in x naught, and then next one the y1, the numerical solution and exact solution. Just compare them and calculate the error, and you can put this in the table. If you don't want to do too much end calculation, you can also implement this using this MATLAB program. So MATLAB programs, I would like you to, MATLAB program will be much easier. In the MathCAD program that I wrote, so I have too many calculations going on. But there in MATLAB, they have a toolbox when you can call the Rungge-Kutta function, Rungge-Kutta function, and just enter the step, size, and the W and the T time, and the step W, the initial conditions. I think this is the initial condition, right? H is a step, T is 0. And T is 0, you can see from here, the initial condition, and T naught is 0. So this is what you're going to do. The first thing we'll do, so this has been done for you. You do again. Practice, practice is required because in the exam, you don't have MATLAB. Do again by hand. And then verify with MATLAB. Tabulate answer. Please be very neat. Tabulate answer, and then make sure you include the MATLAB code. Please do not Xerox copy your friend's MATLAB code. If I see two codes the same, include MATLAB code.